Hi, this is Real Analysis Lecture 13. You can see we're in a different room than usual. That's because I tried videotaping the class this morning, but the camera had been damaged and I didn't get any audio. So I'm redoing the lecture with nobody here except our cameraman later in the day in Lecture 13 for Real Analysis. Main things we're going to do for Lecture 13 are, first of all, we're going to look at the Extreme Value Theorem and outline its proof. I'm not going to go into complete detail about the proof. You can read it in the book. But I will outline the proof. It is something that you could be tested on, and so you will want to really think through it as I think through it. And then we will be looking at something called the intermediate value property, and the fact that derivatives, when they're defined over entire intervals, always satisfy the intermediate value property, even when they don't happen to be continuous, which can actually happen. And then the last thing we'll do is talk about uniform continuity, which is the most important thing for your homework assignment. So let's go ahead and look at the proof of the extreme value theorem. I will again restate the extreme value theorem, both in a form that I showed you in Lecture 12, and also in the form, I'll talk about how it's related to the form in the book. So this is the EVT, extreme value theorem. When I write something like this, I am implicitly meaning that f is a function defined in an interval. I will represent an interval. In general, I will be, could be any kind of interval, an open interval, a closed interval, a half open interval, half closed, including one endpoint and not the other. It could go off to infinity. But for the extreme value theorem, I does have to be a certain kind of interval where I is a closed and bounded interval. So you could add I would equal the closed interval from, say, A to B, if you wanted to, where A is implicitly assumed to be less than B. And we're assuming that f is continuous on I. So I'm going to say be continuous on I. Perhaps it's good to put commas in here. I'm assuming f is continuous on this closed and bounded interval. The conclusion is then, the way I wrote it last time in Lecture 12, the direct image of I under f is also a closed and bounded interval. A bounded BDD interval. How are we doing as far as the size? Do you need to zoom in, or are you okay?
We're good. I wouldn't move any further to the right than the far comma, because then the glare gets hard with this projector on.
Okay, I'll try to.
Unless you use the other whiteboard.
Okay, I'll maybe do that too. Bring this a little closer here. I do use this room for my Calculus 2 class, and taping here is not usually too bad. Zoom in if you need to. So that's the way I stated it, which is different than the book does. I'm going to add some extra comments in here to relate it to the book's statement. So, what does this mean? It means f of I equals some closed interval, say, with left endpoint alpha and right endpoint beta. What does that mean? That would mean there exists C and D in I, which again I'm assuming is the interval from A to B, such that f of C is alpha and f of D is beta. If you're saying the direct image of I under f is this entire closed interval, that means alpha and beta are outputs of f. There's got to be points in I that get mapped to alpha and beta. F of C equals alpha, and f of D equals beta. One more so, We run on sentence here. So f of x values for all x between a and b are going to be between f of c and f of d. Say f of c is less than or equal to f of x is less than or equal to f of d for all x in the interval I. In other words, for all x between a and b. F of c would be called the global minimum value of the function. It occurs at x equals c, and f of d, that output would be called the global maximum value of the function. It occurs at the input d. This is the way our book phrases the conclusion of the intermediate value theorem. I wanted to state it this way, partially because it's going to help us when we get to chapter 8, and because partially it's the form of the theorem that generalizes to other situations, especially within the field called topology. If you ever get into topology, this theorem generalizes. Closed and bounded intervals are examples on the real line of something called a compact set. And it turns out that in more general settings, you can define a compact set in a continuous function. And this kind of theorem still holds. The direct image of a compact set is still compact. All right, but now we're going to look at outlining the proof of this thing. I am going to go ahead and erase it here, but you have it in the record now. The proof in the book consists of two parts. There's two main paragraphs. The first paragraph ends up proving that a continuous function defined in a closed and bounded interval is bounded, first of all, so that the sup and the inf of the set of outputs, the image, exist by the completeness axiom. And the second part consists of proving there's a c and a d that get mapped to the sup and the inf of the image. The alpha and the beta in the notation that I used. So let's think first of all about that first paragraph. I have put parts of this proof on test before, like I mentioned earlier. Usually it's been the second part, which we'll get to, but let's look at the first part. I'm not ruling out the first part as a possibility for the test. So prove, first of all, if f is continuous on the interval from a to b, which is our I, then f is bounded on that same interval. You can prove it as the book does it by an argument by contrapositive. I will phrase it as an argument by contradiction because it feels a little bit more natural to me. And we are just looking at the sketch of the proof, not the actual proof itself for sake of time. And again, you can certainly study it in the book, but I want you to go through the thinking process with me. Try to imagine proving this from scratch. Doing it by contradiction, you could say assume, by way of contradiction, that f is not bounded on I. Okay, what would that mean? You need to negate the definition of what it means for a function to be bounded. What does it mean for a function to be bounded? It means there exists some m, so that for all x in the interval, the absolute value of f of x is less than or equal to that m. So what would unbounded on the interval mean? It would mean no matter what m is, no matter how big it is, you might say, there's some point in the interval where the absolute value of the function is at that point is bigger than the given m. And in particular, you can say for all n in the positive integers, there exists a point xn in I such that the absolute value of f of xn is bigger than n itself. N is a positive integer, which is a real number. If f is not bounded on I, there must be, for each such n, a point like this. Okay? So that's something you can conclude by negating the definition of what it means for a function to be bounded on an interval. What's the next thing to do? This is pretty straightforward, I hope. The next thing to do is based on anytime you encounter having a sequence in a closed and bounded interval, it should be pretty quick in your mind to go back and say, I wonder if Bolzano-Weierstrass might be helpful here, and that indeed is what you want to use. The xn's are all in I. They form a sequence in I, a closed and bounded interval, by Bolzano-Weierstrass. That must mean there is a subsequence to this that converges. You don't know if the xn's themselves converge, but you know they have a convergent subsequence. So let me just abbreviate it. VW, which stands for Bolzano-Weierstrass. Again, Weierstrass is German. W sounds like V. Bolzano-Weierstrass implies that there exists a convergent subsequence of the sequence that is formed by the xn. I didn't use sequence notation, but I could have. X sub p sub n, where the pn's form a sequence of strictly increasing positive integers, that converges. Say to some number z, and it's more than it converges to some number z that's in this closed and bounded interval. What's the only thing we haven't used yet? We haven't used the continuity of f yet. That must be relevant, okay? I am arguing this by contradiction. I would be assuming the function is continuous. If you argued by contrapositive, you'd be trying to prove the function is not continuous on I. The book's argument is essentially the same, except they phrase it in terms of proof by contrapositive. So how's the continuity going to be relevant? You could write the following equation. By continuity, you could say f of z, which is defined since z is an I and f is defined in I. Since z is the limit of the subsequence, you could write that. And the continuity essentially allows you to pull the limit sign out in front of the function. Right? We know we have that fact about f being continuous at a point, and limits of, if you've got a sequence that converges to the given point where f is continuous, then the sequence of outputs also must converge to f of that point. That's essentially what I'm using when I pull the limit sign out in front of the function like this. Essentially, I'm now looking at the limit of this sequence. I don't want to use the green here. The sequence of corresponding function outputs is what I'm looking at here when I write that. But, guess what? Because of this, that's a divergent sequence, which is a contradiction. Because f of z does have to equal something because z is in the interval and f is continuous and defined in the interval. So the fact that this is true means that this sequence does not converge. It can maybe diverge to infinity, but it doesn't converge to a number. And that essentially is our contradiction. This sequence diverges because of this fact up here. You could say, as an inequality, you could say the absolute value of f of x sub pn is bigger than p sub n. P sub n is an integer. Okay, and that would be enough to say this sequence diverges. So there's your contradiction. That would say f is bounded on I. So that's the first paragraph of the proof of the extreme value theorem. Sketch of it. You'd want to give more detail. Although there's a fair amount of detail here, there wouldn't be too much you would have to add. Next, we're going to look at the proof of the second part. The book proves that the sup of the image is attained. There's some d that converges to the sup of the image, beta. Let's do the other one, which again is one of the ones I often put on test. Let's prove there's a sequence, well, let's prove there's a number c that, such that f of c equals alpha, the nth of the image. So now we know f is bounded. On the interval, still a closed and bounded interval. I guess I'm already into the sketch here of the second paragraph. That's going to mean the sup and the inf of the image, the set of outputs, exists. Also called the range, right? Range and image mean the same thing. This is the direct image. It's not an inverse or pre-image like we talked about in lecture 12. Alpha and beta, which is sup, exist, okay? That doesn't mean the image equals the closed interval from alpha to beta yet, though. That's what we have left to do. Claim that there exists a C in the interval from A to B such that f of C equals alpha. And again, the book proves there's a D such that f of D equals beta. This is the completeness axiom here that we're using. Completeness axiom. We're also using the completeness axiom both in the first paragraph and the second paragraph. We're going to use the Boltzano-Weierstrass theorem. The Boltzano-Weierstrass theorem was dependent on the completeness axiom. All right. So how do you go about doing this claim? Well, what you do, let me just consider this visually. Let me draw a number line. I'm going to draw the number line vertically because this is a set of outputs of a function, and so you can think of these as being points on a y-axis, if you like. Here's alpha, here's beta. The direct image we're thinking is going to be the closed interval from alpha to beta, but we don't know that yet. For each positive integer n, I can consider the number alpha plus 1 over n for each positive integer n. So when n is 1, it would be alpha plus 1. When n is 2, it would be alpha plus a half. When n is 3, it would be alpha plus a third, etc. Really generating a sequence of points that converges to alpha, by definition. Since alpha, being the nth of the image, is the greatest lower bound, that would mean any number greater than alpha is not a lower bound of the image. What would that mean? That would mean there's something in the image between these two, and in particular, definitely strictly less than alpha plus 1 over n. There's some point in the image between the two, and definitely less than alpha plus 1 over n, because it's not an upper bound of the image. What should I call that point? How about f of xn? Because it is supposed to be a point in the image of I under f, where xn is an I. Are you getting the feeling of how the Boltzano-Weierstrass theorem is going to be relevant again? Once again, we're going to have a sequence of points in I, a closed and bounded interval. Boltzano-Weierstrass will tell us this has a convergent subsequence. Because these points are squeezed between these two things, and the sequence generated by these things converges to alpha, this will definitely converge to alpha. The subsequence that will converge, generated from this sequence, will be the thing that converges to C, and the continuity then will tie the two together. So again, Boltzano-Weierstrass implies that there exists a convergent subsequence x sub p sub n of the sequence generated by these points. Say it converges to, shall I use z again? I could use something else. Y in the closed and bounded interval. The claim would be that f of y equals c. Actually, I should probably call it c. Huh? Let's call that c. The proof uses the continuity of f. f of c, c being the limit of the subsequence, can be written like this. X can here. And again, the continuity comes in the next step in pulling the limit sign in front of the function. I mentioned that in the first paragraph, though I didn't label it. That's the continuity of f. You're assuming f is continuous on the whole interval, which you do need because you don't know where c is. And then this sequence converges to alpha, so any subsequence of it converges to alpha as well. This equals alpha. And there you have it. That's the essence of the proof. Now, on the test, you want to write out things in sentences, though, as I usually say, you can use abbreviations, symbols like upside down for alls and 3 dots for therefore to help make your writing quicker and easier. Okay? And again, you can study this in the book. But I hope, in going through this verbally with you, I hope you feel like it has made more sense, that you believe you maybe even could think it out yourself, even if you didn't study the book's proof, as long as you practice ahead of time. Next topic is something in the same section, still here, section 3.3, the intermediate value property. It's a definition. Once again, I is some interval here, and a function is defined on I. That's the domain. Here's the codomain. The function outputs are real numbers. I'm not going to assume anything about I here. In the extreme value theorem, you have to assume I is a closed and bounded interval. Here, I could be anything. Closed and bounded interval, open and bounded interval, unbounded interval. Maybe you include the left endpoint, but not the right endpoint. It could be any kind of interval. We say f satisfies the intermediate value property on I. It's important to emphasize what interval you are talking about. You know, functions are more than just formulas or rules. They include the domain. F theoretically might be defined on some bigger interval, and you're only considering some smaller interval here. If for all distinct points A and B in I, I'm not saying whether A is less than B or vice versa, such that f of A and f of B are distinct. I'm not saying which is bigger. And for all values v between f of A and f of B, there exists a C between A and B such that f of C equals v. V is between f of A and f of B. It is your intermediate value that you're talking about with the intermediate value property. The function is going to satisfy this if this is true. So continuous functions on enclosed and bounded intervals do satisfy the intermediate value property. But I want to show you that there are actually discontinuous functions that satisfy the intermediate value property as well. This is a little preview of chapter 4. In particular, this function right here, this piecewise defined function, zoom in a few weeks through there, that equals x squared times sine of 1 over x when x is not 0, and equals 0 when x is 0, so it is defined everywhere. Turns out to be a function that oscillates infinitely often on any little neighborhood around 0, but because of the x squared, those oscillations get small fast enough to actually make this be differentiable at 0. F prime of 0 does exist. Does Mathematica say it exists? Ignore this tag slot number 1 is protected. Maybe I need to clear that. Maybe that's the problem. Clear. Clear F. That might help here. Mathematica claims, nope, still a problem. Mathematica claims that the derivative is 0. Is that right? It is right, actually. This function is differentiable at 0. In fact, we can do a quick limit calculation to believe that. F prime of 0, how are we doing as far as seeing this here? Zoom in, into. It would be this limit. It's an h here, f of h minus f of 0 divided by h. F of 0 is defined to be 0, so this is a limit as h goes to 0 of h squared sine of 1 over h divided by h. One of those h's cancels. And this does have a limit because of the h there. The squeeze theorem for functions like this can be used to prove this limit exists and equals 0. Okay, I didn't prove that, but I hope you believe you could use the squeeze theorem to prove that pretty easily. That means f prime of 0 does exist. This function is differentiable everywhere, including 0. What does its derivative look like? Again, Mathematica to graph both of them. The red graph is the original function. The blue graph is its derivative. They both oscillate infinitely often on any little neighborhood around 0. But the blues graph, the oscillations don't go to 0 in amplitude. It looks like they probably stay near 1 in amplitude, though it seems like the computer might not be completely drawing it accurately. I'm not sure. Turns out this blue graph does have the property that it goes through the origin because f prime of 0 is 0. But it can't be continuous at 0, right? These oscillations are not settling down. The limit as x approaches 0 of f prime of x does not exist, even though f prime of 0 is defined. The derivative is defined everywhere, but it's not continuous everywhere. But it does satisfy the intermediate value property on any interval containing 0. If you look at two function outputs that are distinct for two different distinct inputs, and you've got a value between them, there's going to be some c in between a and b such that f of c equals b. That should be intuitively clear by looking at the graph, because it goes up and down between -1 and 1 infinitely often. Okay, so that's kind of an amazing fact about derivatives. They still satisfy the intermediate value property even when they're not continuous. Even when they exist over entire intervals, but they're not continuous on that interval, they will still satisfy the intermediate value property. Forgot to mention, before I go on to uniform continuity as our last topic, that in the extreme value theorem, you definitely do need the fact that the interval is both closed and bounded. There are certainly simple examples. F of x equals x, I equals the entire real number line that don't have a global max or min value on an unbounded domain. The same function actually doesn't have a global max or min value on a bounded domain if it's an open bounded domain, like the open interval from 0 to 1. The graph does not attain a maximum. It doesn't attain a 1, it's supremum of the image. It's arbitrarily close to it, but it never equals it. These open circles there indicating the point 1, 1, and the point 0, 0 are not part of the graph. So you certainly need the assumption of closed and bounded, and you need the continuity too, of course. You can think of examples where the continuity would fail, and the extreme value theorem would not, the conclusion would not hold in that case. All right, our last topic is uniform continuity, which is mostly about what your homework is on. Uniform continuity, first of all, you should realize it is over an entire interval. You always say a function is uniformly continuous or not over an interval. You never focus on a single point. That's the first thing to realize. The second thing to realize is it's an epsilon delta definition that essentially says that the outputs can be made close when the inputs are close, no matter where they are in the interval. The delta is independent of where you are, essentially, or can be made independent of where you are. Definition, f is uniformly continuous, and we'll abbreviate for sake of time, on I am assuming f is defined on I, of course, if for all epsilon greater than 0, there exists a delta greater than 0 such that, like I just said a minute ago, the distance between function outputs, f of x and f of y, can be made within epsilon of each other, arbitrarily close, by taking those inputs sufficiently close to each other anywhere in the interval. Delta, the same delta, can work for any points in the interval. For all x and y in the interval, such that the distance between x and y is less than delta. Okay, that's the definition. Okay, we're getting used to these kind of definitions. Should be able to negate this definition to prove a function, even if it's continuous on an interval, might not be uniformly continuous on the same interval. And the book has a good example of that. They consider x squared on the entire real number line. It's continuous everywhere, but not uniformly continuous on the entire real number line. However, quadratics like x squared will be uniformly continuous on bounded intervals. They don't have to be closed intervals. Let's consider an example. I'm going to go ahead and erase this. Assuming you've written it down or you're looking at the book. Let's consider a quadratic. Let f of x equal x squared. Actually, let's keep it simple and just consider x squared. And I could pick a closed and bounded interval. I actually can pick an open and bounded interval as well. I'm going to pick the interval from 2 to 7. I'd like to show this function is uniformly continuous. It will be uniformly continuous on this open interval. What's the scratch word for that proof? We're not going to do a full proof. Intuitively, you got to think about this, that you want to make this quantity as small as you like by taking x and y sufficiently close to each other. This is going to be x squared minus y squared, which you can factor and rewrite as the absolute value of x plus y times the absolute value of x minus y. That looks good. This can be made small if x and y are close together. That doesn't look so good, but the interval comes to our rescue. The fact that x and y are in the interval is enough to allow us to put an upper bound on this quantity. The triangle inequality, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. Both of these are going to be assumed to be in this interval, and therefore both of these absolute values are less than or equal to 7. I can even say strictly less than 7. Not a big deal either way. 14 would be our bound. And so what you'd want to do is you'd want to let delta be epsilon over 14 because of this fact to do the proof. Let's imagine doing the proof. You'd say let epsilon greater than 0 be given. Choose delta to be epsilon over 14, and I do want you to note that that's positive. Assume the distance between x and y is less than delta. And also you're assuming x and y are in this interval, which is important, of course. Say this next. The absolute value of x plus y by the triangle inequality and this assumption that they're in here would be less than or equal to 14. Do this calculation and then say this is less than or equal to 14 delta, which equals epsilon by your choice of delta. Okay? So that would be a direct proof that this is uniformly continuous. I'll let you fill in the details. To end lecture here, I want to write down a theorem that is the most important basic theorem about uniform continuity. I call it the Uniform Continuity Theorem. How creative, huh? Uniform Continuity Theorem. I think I remember some of my professors calling it that, but I wasn't sure. I Googled it and did find that other people call it the Uniform Continuity Theorem, not just me. The book doesn't give it a name. Okay, it is I believe on the third page of section 3.4, I'm not going to look up the page number right now. If f, I'm going to go ahead and specify the interval this way this time, is defined in a closed and bounded interval and is continuous on that interval. Here it is essential, once again, that the interval be closed and bounded. Then f is uniformly continuous on that same closed and bounded interval. Right? This is a real fundamental theorem. I call it the Uniform Continuity Theorem, and you can call it that from now on in a test if I say state the Uniform Continuity Theorem. This is the theorem I'm talking about. It is pretty fundamental. The book's proof is pretty important to study. Could it show up on the exam? Well, maybe with some help or maybe parts of it, kind of like the other theorems we've been talking about. It's going to be most useful for us in the section about the chapter about integration to show that continuous functions can be integrated. They are what's called a Riemann integrable, is the most important place where this theorem is useful for us. And I think that wraps up what I wanted to say. I don't remember if there's anything else that I actually said in class this morning when there were actual students in the classroom. I think that does it. I guess I will go ahead and stop.